Welcome to the next lecture in the last week of the course, Basics of Mechanical Engineering 2. We are discussing sustainable engineering and sustainable manufacturing in this week. I have talked about unit manufacturing process. I have talked about life cycle assessment in the previous lectures. In the unit manufacturing process, the various kinds were there, like it was machining, it was casting, forging, assembly, welding, anything that happens at a single workstation is a unit manufacturing process. I will focus this lecture specifically on green machining. There are certain strategies for green machining. When I say green machining, we are talking about the technologies which have been developed to reduce the energy consumption or to improve the quality or to reduce the pollution that is being generated in machining process. So, the contents of the lecture will flow like this: introduction to green machining, objectives and benefits of green machining, conventional versus green machining methods, we will try to see the difference. Then types of green machining that I will discuss very briefly are cryogenic machining, minimum quantity lubrication method, hybrid machining systems, sustainable abrasive machining, bio-based cutting fluid machining, dry machining and magnetic adjustment machining. Then certain challenges which are nowadays coming through these technologies which are there, and future directions. Only a brief introduction. Each of them itself is a big technology on which certain doctoral theses have been written, certain researches have happened in the industry, and people are still developing. For example, in cryogenic machining only, lot of further research is happening, like how to store liquid nitrogen, how to put liquid nitrogen into a portable setup, how to use this specifically for one setup only. When generally liquid nitrogen setup is used, a big setup or big plant is there that supplies this liquid nitrogen to the various workstations wherever this machining is required, cryogenic machining is required. Now, a lot of further research is going on, but I will give you a very brief introduction to what these are. Green machining, it is a sustainable manufacturing approach designed to minimize waste, reduce energy consumption and lower environmental impact. Just a very generic definition as we saw for green manufacturing itself. As industries adopt stricter environmental regulations, green machining is becoming essential for enhancing efficiency, reducing costs and maintaining competitiveness. The integration of smart machining, automation and AI further improves its effectiveness. Smart machining is when the machining tries to understand what is the next step, giving the complete CNC code and try to then understand that this whole component would be completed in one go. That is smart machining system. Automation, using CNC itself is an automation. Then when the component is completed, how do we sort the components? How do we try to take away or take out the defective components? That is automated system based upon sensors. AI would further develop its own programs that will help us to take all the smart machining and automation to a different level. This makes a key driver for the sustainable industrial production. With applications in aerospace, automotive, biomedical, electronics industries, green machining ensures high precision while promoting eco-friendly practices. So, what we do, we eliminate the hazardous byproducts, and we align towards the global effort towards carbon neutrality. I have talked about carbon neutrality, that is net zero, that we talked about in the last lectures, and circular economy principles are further raised. So, this is important in green machining. Objectives of green machining are to minimize environmental impact through sustainable practices, optimize material and energy usage, reduce or eliminate hazardous substances as I just mentioned, improve efficiency and cost effectiveness, support recyclability and circular economy principles. Recyclability, that is when we use the material should be recyclable. Benefits, environmental benefits, reduces waste, emissions, energy consumption. Economic benefits, lower costs through improved efficiency and to longevity. Health and safety, minimizes workers' exposure to toxic fluids and chemicals, because working on vegetable fluids, bio-based cutting fluids which are organic or which are biodegradable, so that is also being focused here. Exposure to toxic fluids and chemicals is reduced here. Regulatory compliance is also there, that is, it supports adherence to environmental standards and corporate sustainability goals. Difference between conventional and green machining, as we saw in the previous slides, environmental impact and waste in green machining is minimal, reduced emissions, sustainable resource use is there. However, in conventional machining, pollution is high, excessive material wastage is there, resource consumption is also high. Energy and cost efficiency is also better, lower energy consumption and reduced cost through optimized machining is there. Cutting fluids, green machining relies upon dry machining, minimum quantity lubrication, cryogenic cooling, and also it enhances safety of the workers. Tool wear and tool life, longer tool life with advanced coatings and eco-friendly lubricants is there in green machining. Material utilization, significant scrap is generated when we talk about the conventional machining. With optimizing cutting paths, we reduce the waste and improve material usage in green machining. This is a green machining type where different kinds of fluids could be used, fluids or cooling conditions could be used. You can see here sustainable cooling conditions, dry machining, that is not using fluid at all. Then carbon dioxide machining using carbon dioxide gas only and no cutting fluid is used. Then we use liquid nitrogen, that is it is cooled. So here different types and tools. When I talk about tools, the equipment or the gadgets which are used to monitor this green machining. Some of the examples here are, for example, for the flank wear analysis of the tool here, we use tool maker's microscope. And in-depth worn tool analysis is taken by SEM or EDS. These images helps us to take the structure of the worn area to the level of nanometers. That is 10 raised to power minus 9. Surface roughness analysis, roughness testers are there. They are developed by Mitsui Toyo or many other companies, which helps us to understand or analyze the surface roughness. Cutting temperature analysis, thermal cameras are there. There are optical thermal cameras. There are thermostat based temperature measuring equipment that could be used. Then maintain or understanding or monitoring the cutting force analysis. Dynamometers are there, majorly manufactured by Kistler. Certain kinds of dynamometers, one which measure in the 3 dimensions, only 3 coordinates, then rotary, different kinds of dynamometers are there that helps us to understand or calculate or monitor or capture what is the force that is applied to do this specific machining. If the force is high, the energy consumption is also high. So that could be monitored here. Next is cryogenic machining as one of the green machining methods. This technique uses cryogenic coolants. These coolants could be liquid nitrogen, that is LN2, or carbon dioxide, that is CO2, which rapidly lower the cutting zone temperature, preventing thermal damage to the workpiece and cutting tool. Key features: it eliminates conventional machining cutting fluids and enhances tool life, reduces friction and heat generation. And fourth is, it helps to improve machining accuracy. Certain advantages as mentioned in the key features itself: high strength materials such as titanium and Inconel could be machined here while maintaining the surface finish, and it enhances the tool durability and reduces environmental impact. Titanium is a tool for machining the titanium. We cannot use simply high speed steel tools. Very high strength tools are to be used. But in cryogenic machining, when we try to use, the tool wear is very less. So that is why the tool durability is high when you try to use cryogenic systems. Limitations: high initial investment, because this requires specialized storage and handling for the cryogenic fluids, and this demands additional safety measures as well, because if leaked, the cryogenic fluids such as liquid nitrogen could be harmful to the person who is using it. So these are stored in very closed or very strong cylinders. Applications: aerospace, titanium, superalloy machining, biomedical industry, prosthetic implants, automotive lightweight alloy machining, and precision manufacturing. These are all applications where cryogenic machining is used. So this is one illustration representing the liquid nitrogen at minus 321 degree Fahrenheit, and this is how does it look like when we are trying to do this cryogenic machining. So this is liquid nitrogen nozzle. So through this pipe, liquid nitrogen is being supplied, and through this nozzle it is being applied at the tool work interface. This is workpiece, this is tool. At this interface the cryogenic fluid is applied, and this dynamometer is measuring the force. There is an IR camera which is also monitoring the temperature. It is only telling that this temperature is 321 degree Fahrenheit. So there are embedded thermocouple, there are rake face, nozzle, cutting insert, flank nozzle. These are all given, taken from a study. Now this setup gives how is liquid nitrogen stored here. It is pressurized container, and from here liquid nitrogen is supplied, and there are components of this container as well. Pressure indicator helps us to control. The pressure indicator and the solenoid valves helps us to control the supply of nickel nitrogen, and it is exactly supplied at the point where final machining has to happen. This is drilling example here. The spindle will rotate and twist drill will try to do machining while cryogenic fluid is being supplied here, and the force is being monitored using a dynamometer, which is all held on bench wise, and this bench wise is further held on a work table. Next is minimum quantity lubrication. Working principle is minimum quantity lubrication that delivers fine mist of lubricant mixed with compressed air directly to the cutting zone, significantly reducing the lubricant usage while maintaining effective cooling and lubrication. In the case of the cutting fluid application, when there is a flood application, the fluid application rate could be 6 liters per minute. 6 liters per minute. This is flood, though this is recycled. On the other hand, minimum quantity lubrication could even supply fluid up till 10 milliliters per minute. This is MQL, minimum quantity lubrication. So here the mist is generated. This mist, how is this generated? Using a specific nozzle through which the compressed air get the cutting fluid passed through, but this is applied specifically in the tool work interface again. So this reduces fluid consumption, minimizes waste disposal, improves chip evacuation, and enhances lubricating efficiency. Advantages: environmentally friendly, lowers machining costs, extends tool life, and reduces heat buildup, making it ideal for sustainable manufacturing. Limitations: it requires precise nozzle positioning for effective lubrication, because when we are talking about minimum quantity lubrication, if this is the tool work interface, this is the work, and here we have a tool that is doing its machining, the mist nozzle has to supply fluid specifically here. So this is mist here. So application, that is the nozzle positioning, and this nozzle has to travel along the tool. Nozzle travels along the tool. This may not be effective for heavy duty machining, as is less suitable for materials with high heat retention. Automotive industry, where gear cutting, drilling, turning, aerospace, milling of aluminum alloys, and general machining of ferrous and non-ferrous metals are some of the examples here. In one of the studies in minimum quantity lubrication system, the energy was captured using the dynamometer. First, the cutting fluid was used to do specific kind of a machining, and for the same machining, minimum quantity lubrication was used. When I say energy, the force was captured using the dynamometer, then this force was translated or converted into the proportion energy that is consumed for applying this force. Now, in this, the overall variable energy savings in a factory is evaluated using equation below, which helps to estimate overall energy by comparing the machining of flood versus the proposed machining of MQL for all the conventional machines. For the whole factory, all the conventional machines, when I'm talking about minimum quantity lubrication, I'm basically talking about in the conventional systems only. So overall energy or percentage saving in overall energy is the difference between the average energy using flood setup minus average energy using the green setup. OG is green setup. Per unit, the average energy of flood setup into 100. This is the percentage of the overall energy saving. Similarly, for the n number of machines, this could be put as energy overall is equal to summation of pi eta I by summation pi, where eta overall is percentage saving in overall energy, pi is percentage processing time of machine I, eta I is percentage saving in energy for machine I is unit manufacturing process, that could be milling, drilling, grinding, EDM, etc. or anything. The rationale for this method is that variable energy is consumed only during processing times. So as I talked about the unit manufacturing process in the previous lectures, so there is factory level, there is production line, and there is unit manufacturing process. So this is specifically I is one unit manufacturing process. When number of unit processes are there, that makes one production line. For example, I1, I2, I3, these makes a production line. And number of I's and J's, I1, 2, 3, then it could be J1, J2, J3. This makes a complete factory. For the overall factory, this percentage could be calculated from the unit manufacturing process. Similarly, the saving in the cutting fluids, for example, as I said, liters per minute and milliliters per minute, around 1000 times down. So this could also be calculated, the difference in the cutting fluid consumed using first setup and the cutting fluid using MQN setup. Per unit, the cutting fluid used in the flood setup into 100, this is percentage saving in cutting fluid. Next is hybrid machining. Hybrid means when we are talking of something between the two things, that is, we try to combine the advantages of two different systems, that is maybe additive manufacturing and CNC manufacturing putting together as a hybrid system, or EDM and magnetic setup putting together as a hybrid system, or cryogenic machining and magnetic based machining putting together becomes a hybrid system. So hybrid machining integrates two or more machining methods such as EDM, electric discharge machining, with ultrasonic vibrations or laser assisted machining to enhance material removal and precision. Key features are, it combines advantages of different machining processes, reduces tool wear, improves material removal efficiency, and enhances surface quality. Advantages are higher precision. It allows machining of complex geometries. Complex geometries means in additive plus CNC manufacturing, if we try to bring them together, it is something like this. We have, suppose, CNC machining here, and we have additive manufacturing here, and I am talking about the productivity in CNC is higher, productivity goes in this direction. However, the shape complexity is better achieved in additive. In between, we can have a system that is hybrid. Machining that takes advantages of both CNC and additive, that is, complex shape could be manufactured using additive manufacturing, and further productivity could be improved using CNC machining. That is, complex geometries could also be handled using additive manufacturing. It reduces machining time, enhances performance in difficult to machine materials. Limitations are high setup costs, complex process control. It requires skilled operations for process optimization. Applications are turbine blade manufacturing. Turbine blade shape is not very easy to reach. Even 5-axis machines find it tough to make specific kind of a turbine blade to get the final efficiency in the propeller, that is the application where the blades are used. So to manufacture these turbine blades, to manufacture this shape, additive manufacturing could be used. To develop the hub further, CNC machining could be used. For biomedical implants, which are also of complex shape, die and mold making, quick die and mold making could be there through additive manufacturing. Through that additive manufacturing, further it could be taken to CNC manufacturing. Micro machining applications are there. Also certain examples of the hybrid machine where this electrochemical micro machining process is assisted by various other machines. This here an assistance is being taken through laser assisted jet in electrochemical machining. You can see laser beam is there and machining is happening through electrochemical, plus laser beaming is also further adding to the machining part. Here an assistance is being taken through abrasives as well. The abrasives are being supplied through this slurry, and in this electrochemical setup, abrasives helps us to further improve the machining. Here ultrasonic assisted electrochemical machining is there, that is electrochemical ECM is going on, but ultrasonic head is also trying to vibrate and try to do more machining using some abrasive slurry here. And also spark assisted chemical engraving, that is also there. So these are some of the examples of hybrid machining here. Next comes sustainable abrasive machining. It uses biodegradable, eco-friendly abrasives in grinding, lapping, polishing processes to minimize environmental impact and improve sustainability. Here the key word is biodegradable or eco-friendly abrasives. This helps to reduce toxic waste, minimize energy consumption and enhances surface quality without the need for the harmful chemicals. Advantages are, it is ideal for high precision applications, it provides uniform surface finish, reduces environmental pollution and extends tool life. Higher cost of sustainable abrasives is one of the limitations. Further, limited availability and requires modification in traditional grinding equipment is also there. When we talk about grinding abrasives which are biodegradable, that is we use natural abrasives, for example walnut covers, for example baking soda. Its availability is very less, though these are biodegradable. These have come from the natural sources only. Applications are optical lens polishing, semiconductor wafer grinding, medical device manufacturing, finishing in aerospace components or so. So this is a generic sustainable abrasive machining setup. Because the availability is very less, so it is put here. You can see a fixed abrasive lapping pad and working platform here. So abrasive loss is there, and through pressure the workpiece is being reciprocated over it and finishing is happening. Next comes bio-based cutting fluid machining. It uses biodegradable lubricants derived from vegetable oils or synthetic esters to provide lubrication and cooling during machining operations. These are non-toxic, these reduce the hazardous wastes, enhances cooling properties and prevents workpiece corrosion. It improves cooling efficiency, and biodegradable lubricants could also be used with MQL system as well. Enhances workplace safety, extends tool life and reduces dependency on petroleum based fluids. One thing is the long term disposal of the cutting fluids which is there for the synthetic cutting fluids. That is a harm to the environment. Second level is, or the lower level is, while machining, the cutting fluid turns into mist, and that mist is harmful to the worker who is working. If this is vegetable oil, it is less harmful. So it extends or enhances the workplace safety as well. Limitations are higher initial cost compared to conventional synthetic coolants, limited commercial availability, and may require adjustments in fluid delivery systems. Not even commercial availability, there are also political system or regulations as well. Cutting fluids are somewhere not allowed to be used for manufacturing purposes, because those are meant for the edible purposes only for food. Applications are automotive engine components machining, medical device manufacturing, precision machining of steel and aluminum alloys, food grade applications, etc. If not using the bio-based cutting fluids, there are certain hazards of non-bio cutting fluids, that is synthetic cutting fluids. So hazards of non-bio cutting fluids are hazardous aerosols which are generated, which I just mentioned. The environment across the machine becomes harmful. Through ingestion it goes inside, and there is a chances of cancer as well. Inhalation or dermal contact, environmental hazards, DNA damage, skin irritation, specifically irritation across the eyes, that is there, lung and heart disease, soil contamination due to disposal, that is there. So use of non-bio cutting fluids after machining and during machining. During machining there is an evaporation in which operator gets certain diseases such as lung cancer, respiratory issues. I would put here as eye rashes and so on, etc. And when these are disposed of, these are contaminating cutting fluids which creates water pollution and soil pollution, that is health effects and environmental destruction. And cleaning of these fluids, that is the treatment, also needs cost and energy. So that is why biodegradable cutting fluids are focused. Another alternative is dry machining, though not applicable in the materials where the thermal properties or thermal conductivity is very low. For example, in titanium, dry machining cannot be done. But generally, dry machining is not using cutting fluid at all. It eliminates the use of liquid coolants by relying on advanced tool materials such as coatings, optimized cutting parameters to manage heat generation. Key features are it reduces environmental pollution, eliminates coolant related costs, improves work safety, and enhances machine efficiency. Definitely, it is cost effective, eliminates coolant disposal issues, environmental friendly, and minimizes contamination in sensitive applications. Limitations are because cutting fluid is not used at all. There is no lubrication and there is also no heat loss that goes to the cutting fluid. The heat resistant cutting tools are only required. This is very important here. It may lead to higher tool wear in aggressive machining. Only for finishing it could be okay, and it is less suitable for heat sensitive materials, which I just mentioned. Applications are in aerospace engineering, for example, machining of aluminum, titanium alloys, automotive engine components, and electronics, that is circuit board fabrication or so. So, positive impacts of dry machining, negative impacts of dry machining. Productivity reduction is there, that is a negative point. Poor product quality could be there. Dry dust generation could be also there, because for example, in grinding, when we use dry machining, a lot of dust would be generated. And when we use flood application, this will flow with the cutting fluid. So that is not there, so dry dust is generated. But positive impacts are clean and healthy work environment, no coolant emissions to environment, no cost for coolant and its maintenance and disposal, meeting environmental regulations. So these are heavy. Next is magnetic assisted machining. When we use machining using magnetic assistance, the tool is magnetized, specifically in reamers. The cutting edge is having longer tool life. The reamers are magnetized, and when magnetized reamers are used, reamers are the finishing materials, finishing for the finishing of the holes. The reamers are used after drilling of the holes. So those are magnetized. Working principle is use magnetic fields to control the movement of abrasive particles or machining tools, reducing friction, improving material removal efficiency. It enhances machining accuracy, improves tool life, enables non-contact machining for delicate components. Advantages are it is ideal for precision machining, reduces tool wear, provides better surface finish, and minimizes mechanical stress on the tool. Limitations are requirement of the special equipment when we try to use magnetic resisting machining, and limited to materials with magnetic properties only, that is ferromagnetic materials are only used, may not be effective for non-ferrous materials. Applications: precision manufacturing of micro components, biomedical implants, aerospace parts, and high accuracy electronic components are there. In magnetic resisting machining, what is there? So there is a workpiece and there are two magnets. This is north pole, this is south pole. In between we have magnetic abrasives. So this is MAF, that is magnetic abrasive finishing, in which the tool and the base are magnetized so that these abrasives are held in between, and these magnetic equipotential lines helps us to control it in the confined area, and finishing is happening through. This is, this is finished part and this is unfinished. Process parameter optimization, whatever kind of the technologies we use, majorly it will come down to, it boils down to the parameter optimization. If we are using a hybrid machining system, for example, if I am taking assistance of laser in electrochemical machining, the parameters that what intensity of laser would be used, what would be the voltage in electrochemical machining, what kind of the dielectric fluid I am using, all those are the parameters which would decide the final machining output which I need to do. Some of the examples of the parameter optimization I will just discuss here, and that is the most important part whatever we do. Process parameter optimization. Process parameter optimization reduces energy consumption while maintaining efficiency. Manufacturing requires substantial energy, machining parameters directly affect power demand and processing time. This is very important. Machining parameters directly affect power demand and processing time. Optimizing these parameters minimizes energy use, lower costs, enhances sustainability, and milling parameters influence energy consumption determined by machine power demand and processing time. Power demand consists of constant, that is computer, fans, lighting, which are our facilities in the manufacturing concern, and there are variable costs. For example, spindle, table drives, components. In any of the system there are variable and fixed costs. For example, fan, room lighting, these are all kind of the permanent. Now while recording, the camera is being used, the camera energy being used in camera, that is a variable cost. Only variable power depends on the process parameter. Processing time is dictated by the feed rate, spindle speed, feed per tooth and fluids. This when we talk about machining, these are parameters which determine our processing time. The process parameters, it is to be optimized in a way. Feed rate is to be fixed to a specific level, spindle speed, feed per tooth, and kind of the fluids in drill. These are all the process parameters which are taken, and the output or responses which determines what is the optimized value could be roughness value, or I will call it at surface roughness, then tool wear. When we are talking about sustainable engineering, I will take here also as energy consumption as one of the parameters, and waste generation as one of the parameters. The roughness value is as desired depending upon the surface finish we required. Tool wear has to be minimum. Energy consumption has to be again minimized, and waste generation also has to be minimized. And from the economic viewpoint, if I try to put, there could be cost, or I would say profit. Profit is to be maximized. But there is one example here which is taken from a study given in this source. Higher feed rates reduce processing time but increase power demand. 3 machining regions of the experiments taken by this researcher is the region 1, where faster feed reduces energy per unit. You can see this is energy consumption of components with constant power demand, and this is energy consumption of components with variable power demand, and this is total energy. The region 1 is here where faster feed reduces energy per unit. Region 3 is there where slower feed lowers energy. In between we have region 2 where energy remains stable. So the lowest energy that is consumed is at this point here. So this is energy per unit manufacture. In green machining, influence of process parameter on the energy per unit manufacture. Parameters are feed rate, spindle RPM, feed per tooth, number of fluids in case of drill or in reaming. Time per unit and power demand are the factors which are taken, and energy per unit is a response that is taken here. So high speed cutting is more efficient than conventional machine cutting. This was the output taken from this study. Increased power demand is offset by shortened cutting time. Coated tools enable high speed cutting with minimal wear. If coating energy is negligible, high speed cutting is optimal. Future studies should explore coating variations and their energy impact. That is, coated tools, as is represented or presented in the previous slide, is one of the techniques to have green machining in case of dry machining. Challenges and future directions. In sustainable or green machining strategies, high initial investment is always there. Sustainable machining technologies are sought and high initial investment is there. Need for skilled operators to handle advanced eco-friendly processes is here. Limited availability of fully biodegradable and sustainable cutting tools, not even tools, I will say materials. These materials could be tools, fluids, coatings, gases, etc. They are limited. Future outlook: development of bio-based lubricants and environmentally friendly coatings are being developed. Integration of hybrid machining systems combining multiple green technologies is being developed. Use of AI and IoT driven monitoring for energy efficient machining is there. Advancement in smart machining tools with self lubricating and self repairing capabilities there. Widespread adoption of Industry 4.0 to enhance precision and minimize waste in manufacturing is there. With this, I am closing my lecture. I will talk about some green metrics in the next and the last lecture of this week and of this course. Thank you.